Hey scientists, Mr. Peluso here, how you going? So this video lesson is going to be on the concepts of boiling and evaporation. So let's get into this one. So what we're going through today is we want to define evaporation as the change of state where a liquid turns into a gas at the surface of that liquid. We want to understand the terms melting point and boiling point. So the concept of evaporation, we can consider a beaker of water at room temperature. So here's my beaker, and here's the water inside, filled up closely to the top. Now, what's actually going on inside that beaker, let me just move my face a little bit, is that the molecules of water are moving around at different speeds. Some are moving fast and some are moving slow. So we can see a body of water, and obviously we can see it as water, but that water is made up of water molecules or particles of water. Now, the molecular model for water looks something like this. So you've got an oxygen atom connected to two hydrogen atoms. A water molecule is nicknamed the Mickey Mouse molecule. I guess you can kind of see it. If you turn that upside down, it kind of looks like Mickey Mouse. But that's what your water molecule looks like. So there's millions and millions of these water molecules inside this beaker of water right now. Okay, so if we look at this graph here, we're graphing the number of molecules at a particular speed, and we've got a normal distribution bell curve here. So the x-axis is looking at the speed of the molecule. So what this is saying is most of the molecules are moving at an average speed, okay? Not too fast, not too slow. There are a few molecules, as we go to the left-hand side, that are moving slow. So the molecules near this end would be moving very slow, and there's very few of those molecules. There's also very few on the other end of the curve that are moving very fast. So the point I'm getting at is not all molecules are moving at the same speed. Where evaporation occurs is if a molecule is at the surface of that body of water and it's moving fast enough, it may escape the liquid. Now, we're simplifying this concept a little bit, but essentially what's happening is it gets to the top, and if it has enough energy, it's moving fast enough, it kind of is able to get out of there. And that's what's called evaporation. So if I'm zooming in on this little spot here, we can see all of these individual water molecules, and the arrows are, they're kind of vector arrows, and they're showing where that water molecule is moving. See that Mickey Mouse shape there? So this water molecule is moving this way, and it's moving kind of fast. This molecule is moving this way, and it's moving faster because the arrow is longer. This one's a bit slower, etc. And we can see if the surface of the water's here, this one is moving faster than all the others because the line's longer. It's moving in the right direction, it's able to escape, and that's evaporated. So since the average speed of the remaining molecules must now be lower, so what I'm saying is if the faster ones are able to kind of escape, then it goes, I guess it makes sense that the ones that are left over are a little bit slower. Therefore, the temperature of the liquid drops. And this is because temperature, so thermometer, the temperature scale for what we use in Australia is degrees Celsius. There's also degrees Fahrenheit used in America, degrees Kelvin, which is used for a lot of science applications. So what I'm getting at is, since temperature is a measure of the kinetic energy of the molecules. So kinetic energy, as we know, is moving energy. So the more that they're moving, the more kinetic energy they have. So if the faster ones are gone, the ones left over have less kinetic energy, therefore a lower temperature. And it kind of makes sense over time. An object or a body of water that's kind of hot, if that's left, think of it kind of the steam coming off, that's that evaporation happening, everything else will lower in temperature. So there are ways that we can speed up this process. Evaporation can take place at any temperature. It doesn't matter if it's boiling hot or relatively cool. To increase the rate of evaporation, we would increase the temperature. So if we put a Bunsen burner underneath a beaker and heat that body of water, the temperature will increase, you're going to get more evaporation. Eventually, all the water would evaporate if you leave it for long enough. So when you're heating using this Bunsen burner, we're providing that heat energy to the bottom water molecules, the ones that are kind of near the bottom of this beaker. And what's happening is that heat energy is being transferred into those molecules in the form of kinetic energy. Now they're moving fast and they're going to start moving, and you're going to get a bit of a circular movement. It's called a convection current. And that heat is going to spread all the way to the top, and then those molecules that have enough energy, they will escape. If we increase the surface area, we would also increase the rate of evaporation. That's because now there's more surface for more water molecules to be able to reach that. So with this shape previously, there's only a certain number of molecules that can be on that surface at one point in time. If we make that surface wider, then there's more opportunities for those molecules to escape. If we increase the airflow over the surface, that can also increase evaporation. That's why our bodies are designed to sweat when we exercise, because that sweat, when the air kind of flows over your body, the water evaporates and that produces a cooling effect. So that's designed to obviously cool us down. So if we increase the airflow, that means the molecules are carried away before they can fall back into the liquid. So essentially they're kind of near the top. Some of them might go out and then lose a bit of energy and go back in. That's basically what happens. You get a bit of evaporation and a bit of condensation when the gas molecules turn back into liquid. Evaporation, condensation, evaporation, condensation. But if there's a bit of wind, evaporation, they get blown away. If we decrease the humidity of the surrounding atmosphere, so humidity, think of like a sauna, that would be or a greenhouse, that would be a humid environment. That also increases the rate of evaporation. And what that does is it stops the water molecules from the atmosphere entering the liquid. Now, boiling. So boiling, we talked a little bit about boiling before. So obviously cooking involves a lot of boiling, making some pasta, delicious. But we've got our Bunsen burner here, and I'm sure you've noticed when you're boiling water, you see these bubbles coming up, and that's how you know, okay, the water is close to boiling, the water is boiling because those bubbles are coming to the surface. So my question is, what's in these bubbles? So boiling occurs when vapor is produced in the body of the liquid. So water vapor, we're thinking like steam, okay? So what's in these bubbles? The bubble contains water vapor, not air, okay? So air has a mixture of gases in it. We breathe in oxygen, that's a gas that's in air. We breathe out carbon dioxide. There's another element called nitrogen, which is in the atmosphere as well, or it's in the air, sorry. But when we're boiling something, it's just water. There's only water in here. There's actually trace elements of other substances as well, but just to simplify, it's just water. And these bubbles are bubbles of water vapor. So that's water that has turned into a gas. It has already evaporated and it's coming to the surface here. So this will only happen at the boiling point of the liquid. Now, what's the boiling point of water? At what point does water turn from a liquid to a gas? Do you know the answer to this? I'm hoping that you do. I'm sure that you do. The boiling point of water is 100 degrees Celsius. So that's when you'll get these air vapor bubbles. And water will freeze at 0 degrees Celsius. That's where the whole temperature scale came about. They looked at water, and water changed at these temperatures, and they said, all right, when it starts boiling, we'll make that 100. When it's freezing, we'll make that 0, and then we'll just fill in everything in between. So that's our temperature scale. So let's summarize. Evaporation only takes place at the surface of the liquid, and it can take place at any temperature. It's when the water molecules escape the surface of that liquid. The concept of boiling is when vapor is produced in the body of the liquid, and this only happens at the boiling point of the liquid. And for water, the boiling point is 100 degrees Celsius. Boiling means bubbles. So if you get that, you're doing really, really well. A couple of quick questions. Which of these diagrams represents a liquid evaporating? A, B, C, or D? The answer is C. I've already got it highlighted so you can tell. How can you tell that it's C? A, we've got particles that are kind of near each other, close together, but it's a little bit messy, a bit unordered. So that would be representative of a liquid. B, we've got the particles arranged in a, I guess, well, it's a cube, but it's an ordered, structured formation. That's the word I was trying to think of. An ordered, structured formation. So that would be a solid. Okay. D, we've got the particles or the molecules that are kind of far apart and they're random in their arrangement. That would be a gas. So C is kind of a little bit of A at the bottom and a little bit of D at the top. So that would be a liquid evaporating up the top. Cool. So let's look at these here, these beakers. Match the three diagrams to the three observations listed below. I know you can't read all of them. My face is in the way. Observation 1. When I melt an ice cube, it takes up less space than when it first came out of the freezer. When I melt an ice cube, it takes up less space than when it first came out of the freezer. So which one do we think is melting? So it's obviously B or C because that's change. So which one takes up less space? I think it's C because C, the beaker is more full at the beginning and less full at the end. And that's because water does this kind of cool thing. It's one of the only substances that actually does this. When it is a solid, the particles arrange themselves so they're kind of further apart. So anything with water in it will expand when it's frozen. And you might have seen that when you put a drink bottle in the freezer and it's kind of, exploded out the top a little bit. So that can happen. So I would say C for that one. Observation 2, when I heat water, it gets bigger or expands in the container. So that looks like option B because we've got the water here and then we're heating it, which gives it more kinetic energy, so more movement. So those particles are now moving more and we can kind of see that they're spaced apart more. That's because they've got a lot of energy. They want to kind of move everywhere. So I'd say B best explains that. Observation 3, when I put some methylated spirits in a beaker, it evaporates. So that would be some cleaning alcohol. So we've got option A is the only one left, and we can see the particles and they're starting to evaporate, which means you've got the ones at the surface that have enough energy to be able to escape. They're the ones that are moving up. And that's it. So guys, I think I'll leave it there. Thanks for watching the video. So I'm going to get you to attempt the evaporation and boiling worksheet for me. You can do that on the Word document, which is in Sector, on the computer, sorry, or you can print it out. And there's also a survey that I just want you to quickly fill in Microsoft Teams, and we'll be going through the solutions to that in our next lesson. Thanks very much.